So welcome to the Distinguished Lecture Series. Just to remind you and also people online, so this is our lecture series where we invite the main thought leaders of their research fields to come to our institute and tell us about their visions. And so it's my pleasure to present you Keren Bergmann. She's a professor of electrical engineering at Columbia University and also a faculty director of Columbia Nano Initiative. She's also director of Center for Ubiquitous Connectivity by DARPA. And she has won many prizes, amongst them recently the IEEE Photonics Engineering Award and the optical CEK medal, which are very high profile prizes. And I'm very happy to have you here at the Institute. Actually, Keren was here already 30 years ago, working as a summer intern in Gerd Leuk's chair at that time at the university, we found out yesterday evening. So there's a connection to Erlangen. So we are welcoming you and we are happy to hear from about photonic connectivity for AI systems.
Thank you very much. So it's a beautiful place, and of course to get to see the new, now for me new, but not so new, Max Planck Institute. It's wonderful, really amazing. Okay, this will be a little bit more systems-oriented talk. So please feel free to interrupt if there's any questions along the way. I don't mind to keep it informal. So I'm sure everyone is aware of the revolution that we're undergoing with AI systems. Many charts like this have been out there. I just want to point out a few things. So of course, this is showing the amount of compute that's going into AI. And I'm only showing the training in this case, because that's really the most compute intensive part of the AI, right? Training the big, large learning models, right? The LLMs. And you can see some familiar things over here, right? Everybody knows GPT. Here's Grok, DeepSeek, right? The Chinese algorithm that had a big impact, a big splash about a year and a half ago. So what's happening here is, first, let's look at the years. So this is a very short period of time, right? About a decade or so. Really, there was almost an inflection point between 2018 and 2020. So maybe 8 years ago. So really things started to accelerate. And I want to point out that the vertical axis is on a logarithmic scale. So this is a very short number of years, logarithmic scale, okay? This is a big deal. So we've not seen anything, at least in my career, that has accelerated this much this quickly. So when everybody's talking about AI, there's something to it. I mean, we've not seen, what's happening is essentially things are increasing by about an order of magnitude every year. I don't know of many things in physics, science, technology that have actually gone this way. Is it slowing down? Not quite yet. Not yet. I mean, definitely there's lots of changes. We're going more from training to the domain-specific inference applications, and many things are going on. But this is big. All right. So let's keep all of this in mind. And what I'm interested in, I'm a optical communications person, photonic interconnects, and so we are interested in what's happening to the communication with these large AI systems, and what can photonics do to impact these systems. All right, so this is going up very quickly. At the same time, another very important challenge is the growth in the energy consumption associated with training these big LLMs, right? How much energy is being spent on AI, essentially. And of course, you've probably heard in the news, the data centers that are being installed all over the world, they're equivalent to all the energy of like Ireland is given as an example usually, because it's a relatively small country. But these are big numbers in power consumption and energy consumption. And, we think about computing and we're like, oh, we see this curve going up, orders of magnitude, and yay, computing is going. But energy is not, is not a sustainable resource, right? And I know we care a lot in Erlangen about sustainability. I had a beautiful hotel where everything is sustainable, so I felt very good about myself being here. Actually, all the way back to 30 years ago, the apartment where we stayed was solar powered, so it was great. We had a little issue with the hot water, so you turn it on, and it becomes very hot, and then you turn it off and it becomes very cold. So there was no in between. But besides that, it was great. It was great. So, okay, so energy consumption, very important, right? So again, what I show here is the years, so about a decade, right? And now let me tell you, this is also on a logarithmic scale, right? Seeing energy go up on a logarithmic scale, not very good, right? This is a very scary prospect, and is it slowing down? No, it doesn't seem to be slowing down. So how much energy is being spent? So let's put it a little bit, for me, it's a perspective, right? So the average electricity used in the entire New York City area, that includes Brooklyn and Queens and Staten Island, even though nobody ever goes there, and Manhattan, is about 134,000 megawatt hours, right? It's up here, so it's pretty high, but just to train Grok 3 is already above that, right? Just one model is already above that. So this is very serious, and that's the reason that there's a lot of work right now on building data centers that are maybe nuclear powered, other energy sources that are powered. Where does this end? Where are we going? Not an easy question to answer. All right, and then more specific to this talk, what can photonics, right? We're interested in photonics and light. What can we do on the energy consumption side of the issue? Okay, so let's look at where is the communication? In these big, we have a lot of compute, we have memory. Where does the communication come in, right? Where are the bottlenecks, and what can we do about it? So typically these large systems, and I just go back here. So, the Grok 3 was trained on 100,000, boxes of GPUs, right? Not even not single GPUs. These are boxes, H100s. Now we're up to the B200s, the NVIDIA, box essentially. So these are a very, very large number of compute, and when you have a computing application, a workload that's spread out over so many compute elements, right? They need to talk to each other. There has to be communication that exists between them, and that's where the problem comes in. And so let's look at the communication. So if we are inside what we call the socket, and the socket looks like basically GPU or a small number of GPUs, right? And they're sitting on like an interposer. They're basically, kind of this size, right? I have some pictures, I think, a little later on. And so they're all integrated in this kind of 3D. There's a lot of 3D integration, heterogeneous integration. You have your GPUs, you have your high bandwidth memory, HBMs. Sometimes you might have a CPU in there, but this is kind of the basic structure. And so inside this little, very sophisticated multi-chip module, you have a lot of bandwidth. Look at these numbers. terabytes. So terabytes, not terabits, terabytes, right? So 80 terabits or so, even 100 terabits is not unusual inside this chip. So this is tremendous amount of bandwidth. However, as soon as we go out, now we have to connect them together, right? Remember, we have 100,000 boxes that we have to connect to each other. So when we go outside of the socket, we drop by about a factor of 10 already. You know, we take a hit about a factor of 10. And then when we really scale the system, when we really go to the 100,000 or 20,000, whatever is the size of the system that's built, we take a huge drop by almost a factor of 100. So from inside the socket to across the system, there is a tremendous drop in the communication, right? We fall off a cliff. Why, right? That doesn't seem like it would be a good thing. Essentially, it's the limitation of the electrical communications. To send the signal over that kind of longer distance requires amplification. You know, the electrical signaling is very difficult, and power consumption, right? It takes power consumption, and also the density. The density of the bandwidth is significantly reduced. Density means how many terabits can I put in a millimeter, essentially, you know, the bandwidth density. So all those things are very, very difficult in the electronic domain, and so they just fall off a cliff. So what does that do to the system? It makes the system very, very inefficient. So one of the reasons that you see this energy go up, you know, almost, you know, indefinitely, is that, of course, you know, the compute itself, the GPUs are very power hungry. They have to do their work. The memory, you know, consumes a certain amount of power. But now when we try to connect them together, and they need to efficiently work together to finish the workload, to solve the application, to solve the problem. And so this GPU on one side of the system needs to access, you know, memory space all the way on the other side of the system, perhaps from other. And so what they do is they start from a place where they have 100 times the bandwidth. They try to maximize the amount of communication, of course, that they do inside the socket. But then they have to fetch some data, all the way from the other side of the system. And then the bandwidth is dropping by a factor of 100 or so. And so while you're waiting for the data to come from far away, your memory space to come back from far away, you're sitting there idling, wasting a lot of energy. So there's tremendous amount of extra energy that's wasted. Plus you're connecting to another box of GPUs and trying to get to their memory space. So it's you have these big boxes that have all kinds of stuff in them, GPUs, memory, you know, sometimes FPGAs. And there's imagine like a little straw of bandwidth that's connected. And you're trying to put them all together, 100,000 of them together. And so drinking the data out of that tiny, tiny straw is tremendously inefficient. Why do we have systems this way? As I mentioned, it's the power consumption and the cost, right? The cost of, putting electrical connections, sometimes fiber optic connections, but still pluggable fiber optic connections that are, much lower bandwidth than the integrated. I will talk about the integrated photonics in a little bit. Is the driving reason. So this is where the systems are today. Great. So let me show you an example of this exact problem and how in China they sort of try to address it with some interesting technologies, optical technologies. Okay, what am I showing here? You might have heard on the news that the US, has some export control restrictions on the GPUs that we send to China, right? That we sell to China. This is not a political talk. It is what it is, right? So in the US and other countries like Germany, of course, we have access to the best GPUs in the world, which are right now, they're the B200s and getting better, right? Very, very massive GPUs. So the B200 over here, right, is made by NVIDIA. Each of the chips has 25,000 teraflops, right? Just that dual chip, the dual B200 has 25,000 teraflops, 2.5 petaflops. I remember when I was an early stage researcher, we went to a whole conference where the goal of the conference was petaflop computing, right? We didn't think that we would ever get to a petaflop computing. It was like somewhere in the future. Now we have it on a chip. Okay, this is the amazing thing. Okay, and it is very impressive to have it. It has a certain amount of memory. It has a certain amount of bandwidth. These are, let's put these aside for now. The chip that the US is allowed to sell to China, what they do is they dial it down, right? We give them a more inferior chips. No comments on the politics, but basically the chips that we sell to China is about 3 times less performance than what is available to the US and other countries, okay? So what do we do, right? In the US, NVIDIA takes their very powerful chips and they connect them with copper, with electrical copper. And they built a system, this is a small system in the scale-up domain called the NVL72. It can go up a little bit more, it's okay. But it's only 72 because it's limited by how far you can reach with the copper, right? You can't scale much more than that. So what did China do? Huawei built a system called Cloud Matrix, and they took their 3 times inferior chips, right? But they connected them with fiber optics, linear pluggable fiber optics, and they got about 2 times the performance of the NVIDIA system with the 3 times better chips. Then they ran DeepSeek on it, and we know the rest of the story. So everybody was talking about DeepSeek and the algorithm and all of that. But underneath, there's hardware that's using photonics. This is, in my opinion, the first commercial example of a real system that's using photonics in what we call the scale-up domain, like actually inside the box, the system, connecting the GPUs together. Everybody uses fiber optics. You go to data centers, you'll see lots of fiber optics, but that's in the scale-out domain. That's to connect, racks together. This is inside the system. And they were actually able to get better performance. So this is really, really interesting. If you look at the papers, there are some papers on this, right? This is in the public domain. I did searches, I tried to find the word. You look for the word optics, you look for the word photonics, doesn't exist. So very interesting, but we were able to dig this out, and it's in the public domain. I'm not showing you anything that's secret, but they're using linear pluggable optics. Very, very interesting. Okay, so the other big shockwave that happened in our community was last year, actually exactly around this time last year. NVIDIA made the announcement that they were going to use integrated silicon photonics in their systems, inside the socket. And so they showed, this was a big splash, and they showed that, they're using everybody. It was kind of a poorly kept secret that they're fabricating their silicon photonics at TSMC. It's a mature node, right? 65 nanometers, that's a pretty mature node. But of course, they're using TSMC 6 nanometers for the electric. This is in Taiwan. Yeah, absolutely. NVIDIA makes everything at TSMC. Yeah. And so does AMD, and so does Broadcom. Basically, TSMC is the go-to. Yeah. But now TSMC is doing photonics. They've been working on it for a couple of years, but now it's really happening. Yeah. And they're using an old node for photonics. The good thing about photonics is that you don't need an advanced node, right? Because what we care, the photonic wavelength is that we're using here, typically it's either 1.3 microns, 1.5 microns. It's huge, right? So the only thing you care about in terms of the CMOS process is that you have enough that you have enough ability to print the waveguides and the other photonic devices, the resonators, so that you don't have scattering, right? So you have low losses. The other thing, though, is you want to have the advanced tools, right? So a foundry, of course, it's all about the node, right? How precise, 2 nanometers, angstroms now, people are going further and further. For optics, we don't care so much about that, right? 65 nanometers is plenty, right? However, when you have very advanced foundry tools, then you can also make them with very high, very low, I should say, variations, right? So the old foundries, the one that are using, 200 millimeter wafers and 180 nanometer nodes or whatever, they also have old tools. And those tools are not very precise, right? We care about the variations. We want the waveguides, the rings, the Mach Zehnders that we make in silicon photonics to be exactly the same over and over again. And we know in optics, that's where the precision is important. And so it's about the tools. It's about the wafer scale tools that actually matters. So anyways, this was a big announcement. It was made. It was actually made in March of 2025, right before the OFC. If you guys are familiar, that's the big conference for us, OFC 2025. So everybody at OFC was crazy about this. And what they did was they said, we are doing this, right? Until then, everybody was talking about it, but when NVIDIA said we're doing this, that really changed the game. And very importantly, here's what they're doing. They're not doing Mach Zehnders. They're doing rings. They're doing rings. Why are they doing rings? Rings they're temperature sensitive, they're wavelength sensitive. You just put Mach Zehnders there, they're much better. They're doing rings because this is the only way to get the bandwidth density and the low energy consumption inside the socket. If I use MZIs, if I use, any other technology, really, direct drive lasers, all these other things, they're going to be too large and too power consuming to get to the metrics that I need. Of course, they only showed one ring. In a more recent work, just now that came out in ISSCC, another conference, electronics conference, they showed eight channels. So this is going very quickly, very quickly. Now there's lots of startup companies that are doing this. If you've heard of Celestial AI, Light Matter, I have a company as well that's working on this. So this is a very, very exciting field right now. Lots of action. What they also need, that's missing, is the lasers. Sometimes, people in this field, they came at it from different areas. They're from computing, from electronics, and they're like, oh, silicon photonics, we can integrate everything on a chip. It's beautiful. It'll be just like CMOS. It's great. Oh, we need a laser. They forget that to do photonics, you need lasers. So I know it sounds ridiculous, the Max Planck for light, but to do light, you need lasers. I mean, in this way, the integrated form. So, of course, I'm being silly, but it's a bit of an afterthought, right? And so they made, NVIDIA made this big splash, but where's the laser? So they have some kind of box that's sitting somewhere off the system, and they really need not just a single wavelength laser, they really need multiple wavelength lasers, dense WDM lasers, to make this happen. And there's a story, if you just go to NASDAQ, right, stock market, look at a company that you might know called Lumentum. or Coherent. Everybody knows Coherent, right? They make lasers. Look at their stock price in the last few months. Over the last year, Lumentum went, I think, from 1 billion to 50 billion. What's going on here? Everybody's realizing we need lasers. There aren't many lasers in the world. I'm not giving any investment advice, by the way. But, you know, you guys are optics experts, so you can think of it. Okay, so how do we build these things? How do they work? Our approach, and I think it's you'll see why we are very excited about it, is to use comb laser technology. I know that my colleague, Professor Michal Lipson, was here just last week, maybe. And so we worked together on this with Lipson, Gaeta, and myself on developing these comb laser technology. So this is why is this so interesting? Because we can use a single laser. We still need a laser, but we can generate lots and lots of different channels, lots and lots of different wavelength channels all at the same time that are precisely aligned for our data. And so this is the typical architecture. Imagine that we have, you know, a comb that's generating all these channels, and then we go into our silicon photonic chip. We use these resonator modulators. So they do two things at once. They are resonators, so they resonate at one specific, they're designed to be resonant at one specific wavelength, which means that they are selected. They select that particular wavelength, right? So I don't need to go, if I use the Mach-Zehnder, I know it's very simple, but just bear with me. If I had Mach-Zehnder modulators and I come in with multiple wavelengths, right? I need to first separate out those wavelengths with some kind of a wavelength demultiplexer, right? And why is that not good? It's not good because those WDM demultiplexers are huge. You know, it's hard to make them very small. And then after that, I put these huge, humongous, you know, MZIs. The MZIs are like, you know, we size MZIs in hundreds of microns or even sub-millimeter, right? That's like, forget it. The whole size of the chip is a millimeter, right? So we can't use that stuff because otherwise, if we look at the bandwidth density that we generate, right? It's not just the bandwidth. It's not just that we can run the Mach-Zehnder at 100 gigabit. It's about the bandwidth density. How much can I get in and out of the chip? So having a device that's a resonator does two things at once. It does the modulation and the wavelength selection is very advantageous. So very important. So we use these modulators, and then we have the opposite on the opposite side. We just have filters and detectors, and this is kind of the basic structure. And then, you know, you'll see that there's it's basically by shifting the resonance. Yes, there's definitely there are going to be losses, but it's not like an electro-absorption modulator. It doesn't work on that loss. It's you shift the resonance, and that becomes the on-off. Yes. So there's some tweaks there. What we do is, so there are various designs on the resonator. You can have a ring. What we do, and I find out that this is also down here, we use discs. And discs, instead of the ring, which propagates the light, you know, along the waveguide, the disc it's a whispering gallery mode that we design. Why do we use disc? I'll go into it a little bit, but primarily because you can make it smaller, right? We're trying to make things, optics is way too big. I'm sorry. It's just, you know, the wavelength is just too big when you're thinking about integrating it with electronics. And so everything that we can do to squeeze the size is very important. So this is kind of the result. You can go to sleep after this if you want. But the results are, here's the most important metric that we care about, right? I keep going back to it. It's about what is your bandwidth density, right? How much bandwidth do you have per unit millimeter or per unit millimeter squared? And how much energy per bit are you spending? Those are the two things. And the key is you need both at the same time. If I just wanted bandwidth density at any energy consumption, I could probably figure out a way to do that with electronics, right? You know, electronics on a chip can be very, very good. in terms of the bandwidth density. I can put lots and lots of interconnects, multiple layers. But I need to be able to move that data across the system. And so, doing it with electronics is not going to work well. And let me give you another example. Let's say the pluggable optics, right? Everybody knows the pluggable optics. You have a transceiver. If you go to a conference, they're going to talk about, oh, we can do 800 gigabit per second, in pluggable optics, maybe soon, 1.6 terabit. Not enough, because the pluggable optic is like huge. It's like, it's like the size of a finger or so. And you're like, oh, that's very nice. I can get a terabit from this. No, not enough. We need tens of terabits per millimeter. That's the bandwidth density that we need to get. And at the same time, very low energy consumption. So the only way we can really get there is by increasing the number of wavelengths. If we have a lot of wavelengths, we can modulate each wavelength at a relatively modest data rate that reduces the energy consumption. And if we can squeeze enough of this on the chip, we can get the bandwidth density. So again, what you see here, and I want to say this is, again, a logarithmic scale. So here is some different examples, depending on the number of channels that you used. The greener it is, the less energy consumption. The more green it is, right, the less energy consumption. So this is some of our recent work. We can get very, very low energy consumption, and we do it by using a lot of wavelengths, 80 wavelengths in this case. This is the NVIDIA. It's not bad. It's not bad. They run their modulators at pretty high speeds, and so they're not as energy efficient. But honestly, they're not using a lot of wavelengths because they don't have a lot of wavelengths, right? There isn't available, you can't buy 128 laser source right now in large scale. So that's why they're over here. They would love to be here where the research is, but they're not, they can't get there. Yeah.
The one-dimensional cross-section in the surface of the...
Exactly, it's the perimeter, So this is the most precious real estate on the chip. Because on the chip, you're going to have a lot of electronics that's very, very important, right? The GPUs, the other stuff. And then you have a little bit, you try to minimize how much you have for your I/O. You're not going to use optics inside the chip. It doesn't make any sense because electronics is just too good. Electronics is really good. So it's about moving the data out of the chip, chip to chip or across the system. And so the perimeter is the most important parameter. And that's the most precious real estate. Yeah, exactly. There are other ways, like let's say you want to come from the top, but there's always a trade-off because people want to put your memory integrated on the top, heterogeneous integrated memory, because the memory bandwidth is really key. So it's a combination of understanding the packaging, what's the packaging approach, and where you can squeeze in your I/O. Yeah. So sometimes we talk about millimeter squared, but usually the millimeter is an important parameter. Okay, actually that leads to this picture. So this is kind of where things are today. This is the reason pluggable optics, it's very good, it's very useful. It's going to be continued. I'm not saying that pluggable optics is going out of fashion. It continues, don't worry about it. It's all good. But and this is what this socket, I kept talking about the socket. This is sort of what it looks like, right? You have some GPUs, you have your memory. You can see this is very crowded, right? This is kind of the TSMC, 3D packaging approach that they have, many different things around this. And the idea is that, can we bring the photonics in some way, inside this package? And, should it be 3D? That's what we like to do, so that you can get a lot of density from that. But this is still ongoing work, All right, so let's go back to our story about NVIDIA and Huawei. What if we replaced, we took the best of everything, right? Take the best GPUs in the world, but now instead of using the pluggable optics that Huawei had to use, because that's what's available commercially, we used this new optics that's available. I like to call it embedded photonics, right? Because we're really embedding it inside the socket. Look at these numbers. You know, the scaling is just amazing. And this is all under the same energy envelope that we started from. So we're not spending any more energy. We're just vastly increasing the amount of bandwidth that's available to the system. So now we can basically cut out that 100x drop that we used to have, that we have today in the current systems, right? We went from the socket, to the system. We took 100x drop. We can eliminate it. And I like to say the world is my cache. I know it's a CS kind of joke, right? So I can communicate anywhere in the system like it was my own personal cache. I wish it was cache, with the dollar signs, but it's okay. Yeah. All right, here we go. So you're probably very familiar with the world of silicon photonic fabrication. So today, a lot of the big foundries, the commercial foundries that are doing electronics, I mentioned TSMC, are now doing photonics. Global Foundries is doing photonics. Tower is doing photonics, and others across the world. AIM it's used by IBM in Albany, New York. So it's basically, it does 300 millimeter, right, 12-inch wafer photonics. So big time photonics, but it's a research, kind of like a R&D institute. It's not a commercial entity. So it has the best of the worlds that we care about, which is we can design new things with them. If I work with TSMC or if I work with Global Foundries, which we do, I can't tell TSMC, oh no, change your process, add doping, they're not going to listen to me. But I can work with AIM to do that in a more reasonable, cost-wise. So, but I have access to the 300 millimeter fab. So this is the really, really nice thing. And so this AIM has been around since about 2015. It's a manufacturing institute that was sponsored primarily by the government in the US. And I've been involved with it since the beginning. So it's been a great collaboration. And so usually when you design a chip, any chip, whether it's CMOS or photonics, you do something as a university person, you do something called MPW, right? Multi-project wafer run, which means that you buy a little piece of the real estate on the wafer. I want to buy 5 millimeters squared or 25 millimeters squared, whatever it is. You pay a lot of money, you put some designs, and then 6 months later or 5 months later, you get your chips back. They don't work, and then you realize that you just spent a lot of money on a little piece of silicon. It happens, right? So we do that all the time. What we're able to do now is, instead of just buying a little piece, we get the entire reticle, right? The entire 300 millimeter reticle. And so we can custom design everything. And so we've been doing this for about a decade now, a little bit less than a decade. And so this was our very first full reticle. And so you can see it has, it's amazing. There's almost too much space, right? The students get very spoiled. They can draw all kinds of things. It also enables you to do a lot of statistical work. So you can see what the fabrication variations are across the wafer and all kinds of stuff. It's just, and lastly, the reason it's very interesting is that it allows you to do wafer scale packaging, right? If I just have my little die, right, that I got back from my MPW run, now I want to say, well, let me put an electronic chip on top of it to do some 3D integration. And I go to a place that does packaging and I give them my die, and they're like, we can't do anything with this. We can't align it. We can't. If you give me a wafer, then I can use my 300 millimeter tools. That's why the tools are very, very important. It's all about the tools. The TSMC, even though they have a 65 nanometer process, this is also a 65 nanometer process. It's an old process, but the tools, 300 millimeter tools, are the key to everything. So this was our first wafer. Then we got greedy. We did another wafer and another wafer. And this one is still in fabrication. So it's very, very nice so to do this kind of work, right? This kind of very complex integrated photonic circuitry work, having this capability is game changing for us. And this is just an example here, right? How do you measure all these things, right? You have a wafer, you go to a conventional lab, and you have a little microscope and probes, and everybody's measuring their chips. Okay, there's if you need to measure a wafer, especially to get statistical data, forget about it, right? It's going to take each PhD student a long time. So we were able to procure this. This is a Photonic prober, but it's very specifically designed for us, where we can do RF, DC, and optical, both optical vertical as well as optical, directly to the chip coupling, automated. Everything is automated. So now we can get wafer scale data. It's not as magical as I'm saying. There's a lot of tweaking and things. So there's a couple of PhDs that work with this. It's not, but it's a lot more enabling than we could. All right. So the comb, right? The comb is a really key thing. And so as I mentioned, this is primarily led by Gaeta and Lipson. This is a picture of just in our lab of the comb. It's a very simple chip. It's basically a silicon nitride resonator chip that's pumped by laser. So you still need a laser. But the nice thing about it is that the pump can sit anywhere. It just comes in with a fiber. So it can sit anywhere in the system. And then this little silicon nitride chip is, just has a little thermal control on it. Very, very simple. We are now working on a new project where the comb resonator and the active silicon photonic will all be on the same chip. So right now it's two separate chips. We have the comb and then we have the link. But because silicon nitride is part of the process, part of the CMOS process, it just needs to be a little thick. But that's what we're working on right now. So these are some new results that we were able to get from the combs. So typically these combs run at a certain FSR, right, free spectral range. And so this particular comb was designed to have an FSR of 100 gigahertz. But it turns out that this is from Professor Alex Gaeta's group. They were able to run at different FSR states. And so they can go at 200 gigahertz and 300 gigahertz. And this is just beautiful. We have flexibility in the FSR, and it really helps on the design of the link. So just want to mention that, and it's very high power as well for combs. Okay, the modulators is another key component of all of this, and as I mentioned, we're talking about the disk modulators. Yeah. The power goes up. Yeah, the number of channels goes down because the Q factor is it's just a matter of how many pulses you have running around in that comb generator. So I don't think the device stays the same, but the different FSR states, and so having what does happen though, which is I don't exactly know why, but as you go to a larger FSR, the conversion efficiency from the pump to the comb goes up. It goes up, which is very good because the higher the conversion efficiency, the more energy efficient the link is. That's very, very important part. So operating at the 300 gigahertz is much more efficient. We have an upcoming Clio paper on that where we show that you get much better links with the larger FSR. Yeah, just a little note. The disk, these are the disk modulators. We went through multiple generations of these disks. So what's important about these disks? They're vertical dope junctions. And so the challenge there is you want to design it so that it's single mode, right? So obviously the whispering gallery is not a single mode. The disk is not a single mode device. So it's a challenge. You want to design it so that everything has loss as much as possible except the fundamental mode. And then you want to design it to go as fast as you can, with as low voltage as you can. Oh, and then you need to have thermal control. All in the smallest possible disk that you can. So this is kind of where we're driving, and we're able to get kind of record small disks. This FSR, so you want to get the largest FSR that you can on the disk. And the best that we've gotten so far is about 60 nanometers, which is very nice. We can cover almost the entire comb in that. And then we have new designs where we call them FSR-less combs that just have a single resonance. And by designing, I don't have it in the stock, but basically by designing the coupler, this coupler over here, the curved coupler, you can design it so that through dispersion engineering, so that only one of the FSR lines survives. So we're still on that, but I want to give you understand where we're going. And the smallest that we can make it is about 2 microns radius. So it's small, but we hope to get smaller. Obviously, there's a limit of the curvature. Maybe we can get a solution for the losses there. But here's another important thing. We can get modulation pretty fast, 32 gig, with only 0.4 volts peak to peak. So that's important because it's really CMOS compatible, advanced node compatible. Sometimes people will say, oh, it's made up, it's silicon photonics, so it's CMOS compatible. Okay, but it's not really CMOS compatible if you need 1.5 volts or 3 volts to drive it. Okay, that's not advanced CMOS compatible. Advanced CMOS has very low voltages that you need to work with. Again, we're like really focused on the energy, right? Another big component of the energy is the thermal control that you need to apply to everything. And so we worked with AIM on introducing undercut, so basically drilling holes in the wafer, right? So you have air pockets underneath your devices. So this is an example. So without the undercut, you apply 0, 1 milliwatt, 2 milliwatts, 3, 4, 5, and you tune the disks a little bit. With the undercut, you apply the same amount of power, you can tune a lot more, right? So much, much more energy efficient. And this is about 5x because the disk is so small. With larger devices, we can get up to 20x and higher. So this is another important part. Lastly, with the disks, this is what we learned from being able to do the wafer scale fabrication, right? So when you do wafer scale, you look at all the variations, and if you design rings, you end up having the rings have a lot more variation in their resonant frequency versus disks. And of course, it's very simple, right? The disks only have one diameter that you care about, right? That you design for a specific frequency. With the rings, you have to design the waveguide. You have 2 edges that you care about. So at the end of the day, you design a bunch of rings for your link, and then you make the measurements, and the resonants are like on top of each other, not where you design them. It's very depressing. And then you have to tune them over. The disks, you design them, they're very close, right? So this is fresh. So in this example, we have 64 disks. It's actually more than 64 because we have an extra one. So 4 times 17 instead of 4 times 16 in this particular link. And look, this is measured, no thermal control, just out. And so now we have to do just a little bit of thermal control to tune them over. And that saves a lot of energy for us as well. All right. So we want to go to the 3D integration because we want to combine this photonic chip with the electronics to be able to get the high bandwidth density and so forth. And so this is work that we did also in collaboration with Cornell University. There's Al Molnar is a professor there. He's an electronic designer. So he designed a simple EIC for us in 28 nanometer TSMC, very, very straightforward node. And then we did this package where it's basically the EIC on top of the PIC. So this was the first real demonstration of 3D. Yeah.
EIC and PIC means?
Of course, I'm so sorry. So EIC is the electronic chip, electronic integrated circuit. The PIC is the photonic, photonic integrated circuit. I'm sorry for that. And so basically, you design this particular electronic chip, you send it to TSMC to be fabricated, it comes back. You have to do, there's a lot of work that you need to do here at the interface so that they can bond to each other. And we're trying to make everything as dense as we possibly can. So the pads are about 25 microns apart from each other. So this has to be done with pretty high precision. And so this was like a really exciting attempt to really do this together. And so this work, this is actually the chip. This is actually the electronic chip on top of the photonic chip, 3D integrated, with all the devices. In this case, we have 80 channels. 80 channels. So this is the chip right here. This is a quarter, US quarter. And look at this precision of the assembly, right? So these are 25 microns apart. Before we succeeded in doing this, we tried to do it with not 300 millimeter wafers, and we couldn't get it to work because like there's no way they can get the alignment to work. You can do it even better. 10 microns is pretty good. These days they can do better with hybrid bonding and things like that. So you can get even denser. But this was great, and in this chip we were able to get just over 5 terabit per millimeter. In this case, per millimeter squared, but 5 terabit with this very high density chip. So we took a picture of it. I was giving a talk, and we just got the results. And so I wanted to get a picture of it from the students. And so it was a young student, an early junior student in the lab, and he said, sure, I'll take a picture. And he put this quarter right here for the picture, right? So that you get a sense of how big it is. And I almost had a heart attack, right? Because he put the quarter right on top of the wire bonds. So, but everything was okay. Whew. Everything was okay. It worked. It was okay. It was okay. He survived. So this was great. So the student survived. Yeah. So the student survived, and he went on to do good things. Yeah. So this was great. So this got the bandwidth density, right? What about the energy? Right? We keep talking about the energy. So this is, by the way, this is all 80 channels. In this case, they're only 10 gigabit per second working, but because the circuit was only able to drive 10 gigabit per second, now we can do 32 gigabits. But look at that, 80 channels at 10 gigabit per second, and only 50 femtojoules per bit for the entire chip, the entire transmitter part of the chip. And so this is a record on the TX side. We then looked at the RX side. So on the RX side, the detectors and basically the bit error rate tester is on the chip. It's designed to be on the electronic side of the chip. So it's getting the data right there. But it has a limited amount of memory because of the simplicity of the chip. So we were only able to measure 10 to the minus 10 instead of 10 to the minus 12. That's okay. But look at these eyes. Just, you could drive a bus through these eyes. And so this is just under 70 femtojoules per bit. This is the entire receiver, the TIA, the front end, everything. So TX RX at 5 terabit per millimeter squared, 120 femtojoules per bit. So we were very excited about this result. We're really going there. I see that we're getting close to the end of the hour, so I'll speed up a little bit. So now, we want to do more channels. We care. One of the other things we care about is the losses. Anything that you can do to reduce the losses is a win. Anything. We're fighting losses because the less loss, the better the energy consumption. So we do that. This is more recent results with the higher speed. So the higher speeds are going to consume more energy because the electronics just takes more energy. So it's a little bit different trade-off, but we're still able to get, and this is including the laser. So the laser also takes a certain amount of energy because you have a wall plug efficiency, you have the conversion efficiency, everything needs to be taken into account. But for the entire link, we can get about 300 femtojoules per bit. But this link is going much faster, 32 gigabits per second per channel. So this is more and more of the latest. This is an example of, okay, now what do we do, right? So here's our chip, here's the electronic chip, the PIC and the EIC, now that I explained what they are. And now what we wanted to do was show that you can actually, so we did, so far we did just dummy data, but now we wanted to show like real data. Can you put like real compute data on it? And so, we don't have access to integrating with the GPUs, but we were able to work with Intel to integrate with FPGA, right? FPGA. So this is an FPGA package that's where the entire package is it's almost done. We have half of it done. Is going to be almost 100 terabit package. Now the FPGA never in its life is going to generate 100 terabit of data. It's okay, but we just want to show that we can program the FPGA for something and it comes out the optical side. So that's the goal here. Okay, I'll skip this part, but this is a little bit more back to the system level. So one of the challenges that we have that's growing, you see, this is from very recent, from like 2019 to today, and continuing to grow, is the gap between the compute and the memory. That's, you just cannot put enough memory on this GPUs. There's not enough space. And everybody's fighting this. Everybody's fighting this. And so, you're trying to get, so the thinking is, what if we took the photonics that we have, right? This is the current architecture. They put the memory all around the GPU, right? As much as they can. But what if we took that and we changed it so all around the GPU is just optics? And then you can go, you're not limited by the package anymore. You could just go a little further out and put as much memory as you want. You have as much space as you want because you're not limited by the interposer, by the package. And so this is where we're going now, really increasing the best of both worlds, right? All the memory bandwidth that you want and the capacity. That's the key. Today, we're limited by the capacity. So this is kind of the system architecture. And these are some initial results. And we're seeing that we can get, tremendous speed ups, like maybe a factor of 3, maybe even more than that, speed up on the workload. And what this means is if you get a factor of 3 speed up, you've reduced the energy that it takes to do that computation by that factor, right? It's about how much training you can do per unit joule. Okay, so let's keep going. I'll skip this part. This is about optical switching, but I'm happy to answer questions about that. We're looking at one of the key questions in sort of optical connected computing systems is you might be familiar with papers in the last years about we put optical switches, MEMS, like Google has MEMS switches in their systems, right? And nobody really knows, like, well, how big do those switches need to be? How fast do they need to go? Google is just using them to reconfigure their system and for reliability. But if you put the switches really inside the system, like a fabric, it's not really clear. Do they need to be a nanosecond? That's bad, because if they need to be a nanosecond, it's very hard to make. Imagine making 1,000 by 1,000 optical switch with nanosecond reconfiguration. Very hard. And it's going to take a lot of energy too, which we can't have. You can make 1,000 by 1,000 MEMS switch, yeah, but it can be like a millisecond. So this particular paper examines that and has a great answer on it. I'm happy to answer questions. And so let me just finish up. This is my world that we're working in, and these are the great people. And this is the new member of our group right here. His name is Levon. So thank you so much for listening, and I'm happy to answer any questions.
Thanks a lot for this really impressive talk and also the introduction in the beginning. That was very, very helpful. Are there questions? Yes. I have this thing. I give you the first one.
Thanks a lot.
Yeah.
I would like to go back to the page where you introduced embedded photonics as the best world of both.
Yeah.
From, let's say, the US American GPUs and the Chinese optical interconnects.
Sure. Yeah.
I mean, you've introduced it in the slides afterwards to us, but there seems to be something missing, because otherwise NVIDIA would be selling this to us.
Mm-hmm.
What is missing?
It doesn't it does not exist yet in large scale. Like NVIDIA, believe me, they're intensely, you might have seen just a few days ago, they invested $2 billion each in Coherent and Lumentum. They invested more in IR Labs, another startup company, because to make it at large scale, the ecosystem is not there. Of course, there's some technical challenges that still need to be solved for real. But if it was there and it was at the cost point where they need to have it, they would do it. And they're definitely marching in that direction. The other thing that's also important to keep in mind is that, they're the leader. And so they get to decide what the pace is. Do they need to spend a lot of money on an expensive optical system? Maybe not yet, until there's competition. So I think that's kind of where things are. Yeah, absolutely. But we're going to make it. Yeah.
All right. Thank you for your talk. So my question is, at the end of your talk, you suggested that we could just replace those HBM stacks surrounding a GPU with optical interconnects. But I think one of the reasons why those HBM stacks are so close is just latency.
Latency is important.
Can you comment on latency with your optics techniques?
Yes, absolutely. Latency is important for sure. Latency, it also depends a little bit on the application. So first of all, these are not going to be that far away, right? Right now, you're always going to have some local memory. You have to have that for sure. But if you're going to go, a few more cycles, off the chip, right? The idea is that we can, these guys are really limited by how far you can have these electrical, traces go. But if we go here, can go any distance. Let's say we just want to keep the distances similar, chip to chip. Now this can be much more bandwidth density, and we can now stack HBMs on a whole nother package, and have much more access to more. Yes, you're right. There's time of flight latency that's going to be taken into account, and the work that I went through very quickly, takes that into account, and that's why it's not perfect, but you still get a benefit. And the good thing about so latency is now the new name of the game, and we're very focused on that. Even more than we were before. First, it was bandwidth. We got the bandwidth. I think we can get there. And now let's squeeze out the latency. Yeah.
Thank you very much for this talk. Oh, okay. I just wanted to know, you talked about modulation on each channel, right?
Yeah.
I wanted to know more. How did you get this thermal tuning?
How did I get the what tuning?
The thermal tuning. I thought you used thermal tuning.
Oh, thermal tuning. Yes, yes. So each one of those devices has, So they have. It depends on the process technology. Sometimes you can have metal heaters. In our case, in our technology, we have doped heaters that we design. So here's an example of a filter. That's the easy one to make. And so this is the disk, and this is a doped heater that's sitting here, and then they have some contacts, and basically that's how it's a very, very small amount of current that we apply to it, and that tunes the device. It's more complicated when you have the modulator, because you have both RF that you're trying to get as fast as you can, and so you want to have as many contacts to minimize the losses, and somewhere you want to still get the heater. And so what we've done, I didn't go into it, but we developed a half-etch technology where we can put the heater outside the disk. So now we can make the disk a lot smaller. And still, we still need room for the RF, but we can make it a lot smaller. And the heater is outside the disk with the half-etch, so it doesn't overlap with the RF signals. Yeah. It's like a 2.5, I would say. Not exactly 3D, yeah. Like 2.5. Yeah. Yeah, exactly. But definitely some design innovations and process innovations. This is why I was saying it's so important we're very fortunate to have this relationship with the foundry where we can say, it's not that simple, but we can say, oh, let's do this and let's do that. And they can sort of do it, yeah.
My question is related to the last one.
Yeah.
You showed this undercut.
Yes,
and
yes.
You had this larger shift. So the reason must be that because with the undercut, you reduce the heat conductivity.
Exactly.
That should also slow down.
Yes.
So there's a trade-off, right?
Yes. I think it actually, I thought it speeds it. No, it slows it down. But it's really not a big factor, because the thermal is slow anyway. It's fine. And as long as the thermal drift, the thermal variations that you're going to, what do we worry about? We worry about, the environment. And so the GPUs are somewhere. The GPUs have such, they produce so much heat and so much power, which is fine. And they're cooled, right? They're water cooled and liquid cooled and all kinds of that. What we actually care about the photonics is not actually the temperature itself, but how fast does it move, right? And it doesn't move that fast. It doesn't change like, just because of the physics, it's not gonna change on, more than like sort of tens of microseconds at best. And so this is not a big factor, but you're right, that's a sacrifice. That's a very good point. It was a trade-off. Yeah.
Let me take a question from Zoom.
Oh, good.
So, how are the lasers connected to the photonic chip? Photonic wire bonding?
What, wire bonding?
How are they connected to the chip?
Oh, the wire bonds. I'm sorry. So the wire bonds were used to just connect to the circuit board. In the chip that we made, we had the electronics is 3D integrated. So the high-speed electronics is right on top of the photonics. So it's direct, bonded, the pads are bonded. But then we also have some thermal control that wasn't on the integrated electronic chip, just in a circuit board that we connected with wire bonds to that. So all the wire bonds are just connected to relatively slow circuitry for the control. Yeah.
So the second question from the same person, Arthur Lobo, how do you deal with the thermal crosstalk of heaters? Slide 18.
It's always I get that question a lot, and we actually do not see a big problem. We have the disks. They're very close to each other, and I showed you the very high density. They're 10 microns away from each other. We really don't see, it's very, very localized heating, and it's actually not much heating. The chip is very cool, right? You think about the whole chip is spending 120 femtojoules per bit. It's a very cool chip. Of course, eventually it's going to be near a massive GPU, so that's a different story, but the photonics is actually very, very low power.
Yes, thank you very much for the wonderful talk. I have a question on the power budget.
Yeah,
in your graph, it looked like the comp generation is one of the biggest chunks.
It is, yeah.
And maybe two questions for that. Are you considering, or are you already using dark soliton comps that would be way more power efficient?
Yes, I don't know the terminology as well. I know Gaeta doesn't love to talk about dark solitons. So the combs are quote unquote normal GVD combs, right? Normal group velocity dispersion combs. And so the good thing about them is that you can have very high conversion efficiency, right? You're not limited like the Soliton to very low, lower conversion efficiency, and you're not limited in the power that you can have. And those two things are very, very important.
Yeah.
Now, the other contributors to this large energy, see, now we reduced other things like, it's always like this game, right? The other things pop up like, wow, we didn't know the comb was so expensive energy-wise. So it's the pump laser. The pump laser is a problem because we're just using commercial pump, right? Like a DFB pump laser. And we have to count, everything counts, every joule counts. We have to count what is the wall plug conversion efficiency. You plug it to the wall, you take the electrical, current, and you convert it to light. You can get that better. If you can get semiconductor lasers to be 50% wall plug efficient, this number is going to go down a lot. This number is going to go down, yeah.
And kind of my additional question would be, how much can you reduce the power of the comb? Because if you have more efficient photodetectors...
Yes, everything contributes, yeah. Everything contributes. It's the photodetectors, it's the sensitivity of the electronics as well. So it's about reducing the noise on the electronic receiver. That's another big, huge factor. And that's why as we go to higher data rates, it becomes worse. That's why we were able to get such good results at 10 gigabit per second, because the sensitivity of the electronics was very, very good, right? Low noise, low frequency, low noise, always. High frequency, a little bit more noise. And so but the good thing about optics is you can increase the bandwidth with wavelengths. And so that's really kind of the design space. So definitely anything you can do about the losses, anything you can do about the laser efficiency, even fundamentally, right? I mean, I don't think, right now these lasers are like maybe at best 25% wall plug efficiency. At best, because we're using high power is better, and that's fine. Low power DFB lasers are actually more like 5% or 3% wall plug efficient. So those are some of the considerations that are key. Yeah.
So I will take one more question from online, and then we should also wrap up. Can you explain the yield numbers for PICs and also for 3D integrated chips?
The
yield numbers.
The yield. Oh, the yield. It's very good. I mean, basically, obviously we're not a commercial entity. We're just doing research. But when we fabricate a wafer, we get it has 64. We get 64 copies of everything, and there is the yield is basically every die works. So the functionality is very high, probably 90% and higher. The key is the variation. What's the variation across the wafer? And there's thickness variations and things like that every single thing affects not so much the quality, the devices work, but exactly where the resonance is, exactly where the couplers are designed to. So yeah, I mean, we certainly get great yield for the research that we want to do, and I would just stipulate that the companies, the commercial people, are getting good yield from the silicon photonics for the commercial applications because they're making products out of it. So yeah.
Thank you.
Yeah.
Are there more questions? Good. Then let's thank. Oh no.
One more. Yes.
One more.
The what?
The logo on the upper right.
Oh, we made this up. I had this goes back a little while, but this one is Columbia. This is the Columbia. It's like a hat. Yeah, that's the Columbia. The other one, LRL, Lightwave Research Laboratory. LRL. Yeah. Yeah.
Okay. So let's thank our speaker again.
Thank you.